can see, my presentation today will be on energy production, and obviously not, what we're used to in our current source. And so what I'm going to cover right now is our demand for change, like why would we want an alternative to energy, the potential of using microorganisms, using their metabolic processes and their byproducts, and then we're going to talk about how to extract energy from those processes. So right now we're using fossil fuels, obviously, and it's not good for the environment, and it's non-renewable. So although there might be a ton of oil in the ground and stuff like that, it's still a limited source. And with our growing world, and since the Industrial Revolution, we've been using more and more fossil fuels every year. So our rate just keeps growing, and our supply is going down. Also, in order to get these fossil fuels, it has environmental impacts, and their use has environmental impacts. So, drilling offshore, it damages the environment, like where they're actually drilling, and also with accidents like recent oil spill. It's just not good for marine life and everything else. Also, another harmful side effect of using fossil fuels is greenhouse gases. Does anyone know what that is?
Greenhouse gases are gases that interact with light and the atmosphere, and it makes things hotter, basically.
And it traps sunlight.
Yeah.
So with all the fossil fuels we're burning, it's making a lot of greenhouse gases in the atmosphere, or more than normal, and so that traps the radiated energy leaving the planet, so it heats up the planet, and it's just not good. And according to the U.S. Department of Energy, fossil fuels are 85% of our total energy use in America. There's different categories of energy we can get from microorganisms. As you can see, methane, potential biodiesel, ethanol, and what I want to concentrate on is electricity and hydrogen. I'm mainly going to focus on electricity and how to extract electrical power out of microorganisms, but also going to touch up a little bit on hydrogen. So the way we're going to do this, extract the energy from microorganisms, is the microbial fuel cell. And what that is just like this contraption where you put in biodegradable materials, any kind of organic waste, basically almost anything organic, and microorganisms will eat that, and from there, metabolic processes going on will extract energy. They're in the works and improving. There's tons of different ways, and researchers are touching up on tons of different ways to improve their efficiency. And basically that's just increasing their power output, feeding them less, and getting more energy out of it. Like right now, it's still kind of impractical for to replace fossil fuels, but we're working on at least saving fossil fuels, or supplementing our energy use with stuff like the MFC. Different methods to increase the efficiency would be using different materials to build it, feeding the microorganisms different food, and also enhancing the microorganisms you want with the desired traits via natural selection or genetic engineering. The benefits of this thing is that it's cheap to manufacture, and there's no harmful byproducts. So here's a picture of one. I'll describe the parts and then come back to the picture and show you exactly what it means. Alright, so they all basically have the same components, even though different researchers in different places have done different methods. They're still all basically the same. There's two electrodes, a positive and a negative one, and they're connected by an external power circuit. So you have the anode, which is negative, and the cathode, which is positive, with an external circuit and an electrolyte solution in the middle. And this is where we're growing our microorganisms, is on the anode. And that's key, because that's the negative electrode, and that's key to extracting the energy. So the difference in voltages between the two electrodes and the electron flow in the circuit, this outer circuit, generate the electrical power. So in this picture right here, what's going on is you have bacteria performing respiration on the anode, and what it's doing is breaking down organic materials into CO2 and stuff like that. In the process, it's releasing electrons, and the electrons, since they're negative and connected to the anode, they have a natural tendency to flow along the circuit to the positive electrode, and that in form, we can use that for power. And at the end of it right here, the electrons at the end are reacting with oxygen molecules and hydronium ions to produce water. So you can say you're killing two birds with one stone right there. But so how are we going to get power out of it? How are the microorganisms attached to the anode? Like, how do we get them there? And how do we get, there's tons of cells. How are we going to get, something from each of these cells? And that's through the biofilm. To show you about biofilms, they're everywhere. It's like a big part of bacteria. They're on your teeth when you wake up. It might be not that bad, but when you wake up, it's kind of so brush your teeth. But yeah, so they're everywhere. And what biofilms do is they're microbial communities, and they live in an extracellular matrix of sugars and proteins. So all these microorganisms living together, they'll secrete proteins and sugars, and it creates this outer deal that's kind of like a shield. It aids in attachment, and it also helps them communicate. And what researchers have found is that electrons from their metabolism can actually go through the whole biofilm and onto the anode. So that's how we're getting the electrons out of them. And the electrons are able to be transmitted across the biofilm to the anode via the pili. And as you can see right here, these are the pili. Singular, it's pilus. And bacteria use these for a number of things. They can use them for moving around, grabbing stuff. Also, they're used in conjugation, and that is the transfer of DNA from one bacteria to another. So this can randomly happen. Bacteria can transfer DNA, and different traits are passed along that way. New species are created. And one thing that these pili do that researchers have found is conduct electrons along their length, so it can be passed across the biofilm. And one thing researchers can do, is since these pili are conducting electrons, they can genetically engineer their desired bacteria they're working with to have larger pili, therefore more electron transfer and more power generated. So the future of the microbial fuel cell. So right now, of course, they're not that practical because of their efficiency and the scale of their power production. But maybe in the future, you could have about a 25-gallon reactor of an MFC, and you can just feed it every day to power your house. Another thing they're used for is water treatment. It can aid in the cost of a water treatment facility by producing energy while purifying water, because they can consume the pollutants in the water and shed electrons in the process. So killing two birds with one stone in there. And another thing that researchers have envisioned is like a forest as a power plant. You can have MFCs hooked up to trees, plugged in, and they'll use the sap from the trees as food for the MFC, and then they'll recycle the sap back into the tree. So you're not harming the trees, and you're producing power from them. And it's pretty far off to have a whole bunch of trees in a forest with all these things hooked up, but maybe in the near future we can have a portable MFC that you can just hook up to a tree yourself and charge your cell phone, something like that. So that's useful. So how do we evaluate the MFC? We have this equation right here, the energy conversion efficiency equation, and what this is this is the fraction of energy in a fuel that is captured in the output of electricity. So it's basically how much are you getting out of how much you put in. It's the product of the potential efficiency and coulombic efficiency. Potential efficiency is the fraction of the potential difference captured as useful electrical energy compared to the potential difference between the electron donor and acceptor. So there's microorganisms respiring on the anode. We're taking those electrons away to make energy, but those electrons would have just gone to another molecule as a reducing agent, and that makes energy in and of itself, but we're just kind of stealing it. But that's basically what that is, and it's a percentage. All the units cancel out when you do the work, and this is the equation itself. You can see the power times the change in time in the numerator, divided by the electron equivalence of the donor, and the negative standard gives free energy change at pH 7 between the electron donor and acceptor, and that also is the same as saying the current times the change in time times the measured voltage of output divided by the same denominator. And if you want, they said fuel has something like a 33% ECE output. So because whenever we use fossil fuels like gasoline in our car, we're combusting it and taking energy from the combustion, but it's really not that efficient. We just have a lot of it, and that's just what people have developed. Here's an improvement or an example of genetic engineering in E. coli. Professor Thomas Wood at Texas A&M, saw that E. coli produce hydrogen, and so he wanted to exaggerate this trait. The way he did that is he deleted 6 specific genes in an E. coli's genome, and that increased the hydrogen production by 140. If this were to get better and be on a large scale as a way to produce energy, people would grow crops like sugar cane, something with sugar, and put them in these huge reactors and get a bunch of hydrogen fuel as the output, and it's in the form of a gas, so it's easy to capture. It just bubbles up out of the solution. And so that's one example. An example of electrical microbe, people are researching is Geobacter sulfuriducens, and this is basically what I was talking about, is oxidation of organic substrates, on an anode, and taking those electrons away and making energy with it. And here's one of the stats that people found with this that was kind of up and coming, just better than normal, was 65 milliamps per meter squared of electrosurface. Now still this is like extremely small, not practical, but with further research and optimization, it could maybe be practical in the future. And an example in Mexico of just people modifying bacteria, through genetic engineering is Bacillus subtilis. Researchers in Mexico modify them to directly ferment ethanol from glucose with 86% yield. So there's another improvement. It's just showing that people are making headway, but we still have a long way to go. So that's where we are now. We're on the small scale. A practical switch away from fossil fuels and not using any is very far off in the future. It's not really going to happen until it has to happen. Working on it, but right now we can use it to help us save money. I think the practical thing in using microorganisms for energy is just as a supplement to what we're already doing, like the water treatment facility, and just lowering the cost of running things and maybe saving electricity in our homes, stuff like that. So the whole goal is to get more out of less, and just further optimization, and maybe move to a large scale. And that is all.